How's it going, everyone? In this video, we're going to use the Taylor series to prove Euler's identity shown below. In my last video, I proved Euler's identity a different way, and it was mentioned in the comments that it can be proven using the Taylor series. This is correct, and I'll show you this proof right here. So the Taylor series tells us that any function which one can take the derivative of infinitely many times can be represented as an infinite sum. And that summation is the nth derivative of that function at a particular point a multiplied by x minus a to the power of n and divided by n factorial. Now, this becomes a more simple formula if we expand around a equals 0. If we do that, then we have a simpler formula where we have the nth derivative at point 0 multiplied by x to the power of n divided by n factorial. So what's that going to look like? Well, first we're just going to have the function at 0 plus the first derivative of the function at 0 multiplied by x plus the second derivative of the function at 0 multiplied by x squared divided by 2 factorial plus the third derivative of the function at 0 multiplied by x cubed divided by 3 factorial, and so on. So we're going to use this to prove Euler's formula. And Euler's formula tells us that e to the power of ix equals the cosine of x plus I times the sine of x. So we're going to use the Taylor series to look at what cosine of x is, what I sine of x is, and we're going to show that if we add those, we get the Taylor series of what e to the power of ix is. So let's get to that. The cosine of x is going to be the sum, as n goes from 0 to infinity, of the nth derivative of cosine around 0 multiplied by x to the power of n divided by n factorial. So first we just have the cosine of 0. Then we have the derivative of cosine at 0, which is negative sine at 0 multiplied by x divided by 1 factorial. Then we have the derivative of negative sine, which is negative cosine, at 0 times x squared divided by 2 factorial. Then we have the derivative of negative cosine, which is positive sine, at 0 times x cubed over 3 factorial, and we'll do one more term, which is going to be a positive cosine at 0 times x to the power 4 over 4 factorial, and we can see the pattern here emerging. First off, everything that has a sine 0 is going to get canceled out, because sine 0 is 0. And what we're left with is everything with an even exponent. What we have then is, now cosine of 0, remember, is 1. So we have 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial. And we're just going to have the signs continuously alternating, right? Because the derivative of cosine of x is negative sine of x. So next we're going to have minus x to the power 6 over 6 factorial plus x to the power of 8 over 8 factorial minus x to the power of 10 over 10 factorial, and so on. Now, what will that look like in summation notation? So we have a sum, and here's how we specify that we're dealing with even numbers. We're going to write k equals 0 to infinity, and we're also alternating between positive 1 and negative 1. So we're going to do negative 1 to the power of k. With k starting from 0, it ensures that we have negative 1 to the power of 0, which is equal to 1 first, and that is this one right here. And then we're going to do x to the power of 2k divided by 2k factorial. Okay, and because we're multiplying k by 2, and k is just every integer from 0 to infinity, it ensures that we're dealing with every even integer, right? And that negative 1 to the power of k means we're alternating positive, negative, plus, minus, plus, minus. So that is the cosine of x. Now, let's see what sine of x gives us. Well, the sine of x, once again, we have an infinite sum where we're looking at the sine of 0, but it's the nth derivative of that, multiplied by x to the power of n divided by n factorial. So we have sine of 0 plus the derivative of sine, so that's cosine of 0 times x over 1 factorial, plus the derivative of cosine, so minus sine of 0 times x squared over 2 factorial, plus the derivative of negative sine, so that's going to be negative cosine at 0 times x cubed over 3 factorial, and then the derivative of negative cosine, positive sine at 0 times x to the power 4 over 4 factorial, and we see the pattern emerging here. Okay, now, again, all of our sine zeros cancel out because sine 0 is 0. And what we have then is the odd powers of x remaining. Remember, this is an x to the power of 1, right? Our next term here is actually going to be cosine of 0 times x to the power 5 over 5 factorial, and so on. Oh, that's a 5 here, right? So how would we write this in summation notation? Keeping in mind that cosine of 0 is 1, we have x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, and we're going to have that positive negative always alternating. Again, because the derivative of sine x is cos x, and the derivative of cos x is negative sine x. Okay, so now we just have, again, an alternating positive negative, but with the odd exponent terms. And so what that looks like in summation notation is as follows. We have, again, that sum as k goes from 0 to infinity, and we have that negative 1 to the power of k, and again k starts at 0, ensuring us that the first term is positive. And then how do we ensure that the that everything's an odd number here? Well, that's going to be x to the power of 2k plus 1 divided by 2k plus 1 factorial. Okay, and that is equal to the sine of x. So notice as k increases from 0 to infinity by 1s, well, 2k plus 1 is always going to be an odd number, right? When k is 0, this 2k plus 1 is 1. When k is 1, this 2k plus 1 is 3. When k is 2, this 2k plus 1 is 5, and so on. That's what tells us it's always going to be an odd number. Okay, so that's sine x. What is going to be I times the sine of x? Well, it's just going to be I times that exact sum that we see right here. Negative 1 to the power of k, x to the power of 2k plus 1 divided by 2k plus 1 factorial. So we are going to use this and the cosine that we derived above later on. But first, we need to expand e to the power of ix. Okay, and this is going to be actually pretty simple. Okay, so we have e to the power of I0, which is the same as e to the power of 0, plus the derivative of e to the power of ix, which is I e to the power of, again, 0, right, because it's this function at 0, times x over 1 factorial, plus next derivative of it, well, that's going to be an I squared, e to the power of 0 x squared over 2 factorial, plus I cubed, e to the power of 0 x cubed over 3 factorial. Again, because taking a derivative of this function is just taking that constant, bringing it to the front, and keeping that constant the same, right? So each consecutive derivative, we're just adding another exponent of I. So what does that end up being equal to? Well, e to the power of 0 is 1, right? So we just have 1 plus ix plus I squared x squared plus I cubed x cubed plus I to the power of 4 x to the power of 4, and all of these are also over 2 factorial, over 3 factorial, over 4 factorial. Next it's going to be I to the power of 5 x to the power of 5 over 5 factorial, and so on. How do we put that into summation notation? So that is the sum as k goes from 0 to infinity of ix to the power of k over k factorial. Right? We're dealing with both the odd terms and the even terms. That is e to the power of ix. Now, here's where it gets interesting. We're going to break this down into the odd exponent terms and the even exponent terms. So let's do that. Okay? First, let's add up the even exponent terms. What's that going to look like? Well, we're going to have ix to the power of 2k divided by 2k factorial. And then odd exponent terms, where we have ix to the power of 2k plus 1 over 2k plus 1 factorial. Okay? Now watch what happens when we simplify these. Notice this 2 here. When we square the I, we're going to get a negative 1. All right? So here's what that's going to look like. Okay? For our even terms, we have a sum as k goes from 0 to infinity of I to the power of 2k times x to the power of 2k over 2k factorial plus the summation as k goes from 0 to infinity of I to the power of 2k plus 1 times x to the power of 2k plus 1 over 2k plus 1 factorial. Now, this I to the power of 2k, that's I squared to the power of k. I squared is negative 1. Okay, so this is negative 1 to the power of k. So we have k going from 0 to infinity, negative 1 to the power of k times x to the power of 2k divided by 2k factorial. You might notice that that is our expansion for cosine of x. Now watch what happens here. Okay? This term right here, okay, I to the power of 2k plus 1, that's equal to I to the power of 2k times I, which is equal to I squared to the power of k times I, which is negative 1 to the power of k times I. And that I doesn't depend on k, it's just a constant which can be factored to the outside of that summation. Okay? And then what's left is negative 1 to the power of k. So we have I times the summation of k going from 0 to infinity of negative 1 to the power of k times x to the power of 2k plus 1 divided by 2k plus 1 factorial. And you'll notice that that is our expansion for the sine of x multiplied by I. Let me just remind you of that. There's I sine x. There's what it's equal to. Negative 1 to the power of k, that's under the summation, times x to the power of 2k plus 1 over 2k plus 1 factorial, all of that multiplied by I. Let's look at our expansion for cosine. It's also the infinite sum of negative 1 to the power of k times x to the power 2k over 2k factorial. So what we've just shown is that e to the power of ix equals the cosine of x plus I times the sine of x. Euler's formula, proven using the Taylor series. I hope you enjoyed that, and until next time.